Good morning, everyone. It's the top of the hour. Let's go ahead and get things started. My name is Travis Walbeck. I'm the training manager here at the National Center for Asphalt Technology. I want to welcome you to this month's installment of our From Research to Implementation webinar series. Today, our topic is Balanced Mix Design Lessons and Tips. This is very exciting because there's so many states right now that are working on implementing BMD in some form or fashion, whether they're looking at benchmarking, they're still trying to decide which tests they want to use, or they're already moved into pilot projects. So with us as always today is Buzz Powell. He worked for the Alabama DOT for 12 years and then 2 years in the private sector before becoming NCAT's first test track manager in 1999. He's recently then been our NCAT Associate Director and Auburn Research Professor. From the NCAT side today, we've got Nathan Moore. Nathan joined NCAT as a co-op student back before he even got his degree, and really enjoyed working with asphalt at that point. Went on to finish his bachelor's degree and his master's degree at Auburn University, working with NCAT, and then became a research engineer in our laboratory. He's very passionate about his work. He's got some really fun projects that he's worked on. He's involved with ASTM and AAPT, and I happen to know he's a wonderful father as well. Then our other guest today is Phil Blankenship. He's the president and owner of Blankenship Asphalt Technology and Training in Richmond, Kentucky. Phil is a licensed engineer who got both his bachelor's and his master's degree in civil engineering from the University of Kentucky. Phil in his career has worked in asphalt with the Kentucky Transportation Cabinet, Kunch Pavement Solutions, and the Asphalt Institute. Then in 2017, Phil founded the Blankenship Asphalt Technology and Training, which we lovingly call BAT Labs. So BAT Labs is a testing laboratory that's focused on lab to pavement innovation and product commercialization. Phil has also served on committees in TRB, AAPT, and ASTM. And we love having him as a guest on our webinar series here. So given that, please, if you've got any questions, if you put those in the chat box, then we can try to get to those at the end if we have time. Given that, I'm going to turn the time over to Buzz. Buzz, take it away.
Well, thank you for that introduction, and I'm really excited to be here with everyone today that's in attendance to discuss this exciting topic of things that we have learned through our work with balanced mix design. And I'm even more excited because I'm here with men that are my professional peers and my very good friends, and also my faith brothers. So we're just going to jump right into this presentation and go from here. So those of you who have participated in these webinars in the past know that they pretty much all follow the same flow. At the very beginning, I provide background on research that we've done at the track and kind of how we got here. We have a PI that comes in and talks about the research and the things that we've learned on the track and in the laboratory. We have a subject matter expert come in, and that can be someone with an agency or someone from the private sector to talk about deployment of what we're working on. And then I come in at the very end and try to pull everything together with takeaways. What are the high points that you can take away and implement in your own practice? So as I said, these webinars all start with the NCAT pavement test track. It's our practical proving ground outdoor laboratory for all the things that we study in the laboratory. And we've been operating the track since 2000, rebuilding every 3 years in a nonprofit research cooperative format for many different state DOTs and FHWA and private sector clients. So we have a lot of work at the track in building these essentially these precision test sections where the research outcomes are not confounded by things like poor materials or bad designs or sloppy work, those types of things. And we have a huge library of experience now related to rebuilding test sections and maintaining test sections that really feeds into the subject that we're here to talk about today. So, kind of launching this from the test track, and thinking about how can we use the test track and the laboratory research that we do to make mixes better. And my personal belief is that we should start in the QC laboratory, the laboratory where we're verifying the quality of mix that's actually being put on our roadways. And if we start in the QC laboratory, that's also often the laboratory that our contractors are using to design our mixes. Then we can go from the QC laboratory to mix design approval. You know, what kind of possibly different or higher level tests that we want to run at agencies or with consulting laboratories in order to approve mixed designs. Well, there's a lot of possibilities out there. There certainly were a lot of possibilities out there in say 2012 timeframe. So the state track state sponsors and FHWA and some private sector partners made a big investment in the 2015 and 2018 tracks to vet the testing options that were out there and find out which ones actually relate to performance that we verified out on the track. And the test that we're here to talk about today is ideal CT testing. And if you're not familiar with this at all, I tell everybody all this is another way to look at the unconditioned side of tensile strength ratio testing. The specimens are slightly different thickness, but that is the test that we're talking about in terms of the temperature and the apparatus. So this is a type of a machine that you use to administer this type of test. And this is the old pin plotter that we had at the test track before it was upgraded to a digital model. You put a specimen, 62 millimeter thick specimen in there, slightly different from TSRs, and you break it, you load it all the way out to failure. In the in this case, the plotter plots out that curve, and where we're used to looking at peak value to do our TSR calculations, ideal CT testing looks at the shape of the curve to assess the brittleness or the ductility of the mix. And we believe that the geometry, the shape of that curve, the area, and various curve components tell us if that mix is healthy or not from a cracking point of view. And the peak load from that same test, we think, or I personally think, can tell us a lot about the rutting properties of the mix. You can do this with a plotter, and there's lots of manual methods you can use, but the best way to do this type of testing is with a smart jig that captures all that information for you. These are not in design specimens, so you don't have to put sample mix in the back of a truck and put it in the oven and get it up to compaction temperature. You can take it straight out of the truck bed, put it in a gyratory compactor as long as the mix is hot enough so you're not crushing rock. And then you use this handy dandy Excel tool that Nathan Moore, who's in this webinar today, developed in order to hit 7% air voids very, very precisely. When you do this procedure, it's about 3.5 hours to go from the time the sample is taken to you have numbers, which is we think is a very, very implementable framework to work with. Now, one of the reasons why we're here talking about this today is because the variability in the processes that we use are going to impact us in a more significant way in ideal CT testing than it ever did in volumetrics. And that's because ideal CT testing is very sensitive to the quality of the mix, not just kind of the basic proportioning of the mix. Sampling, the times that you use to stage things, and the temperatures. Nathan's going to talk about that in his portion of the webinar. Higher air voids give you a higher ideal CT number, and so since the specification is 7 plus or minus 0.5%, you're going to get higher numbers when you compact specimens in the higher portion of that range. The mix is going to be exactly the same. It's just going to affect your data a little bit, so you have to know that going into it. And we still have a lot of questions to answer regarding implementation and a really good final specification framework, because contractors test and agencies sample and test, and then we have to have material for dispute resolution. What's the impact of reheating? What's the impact of aging? There are a lot of things that we don't know about this yet, but we do think that we can use this flavor of balanced mix design to make mixes better. And then lastly, the last thing that I'll say is Nathan and Adam in our lab have done really good work with round robins with loose mix versus pills that I think have gone a long way to inform him. When we're talking about balanced mix design, we often focus on binder content because that's kind of the easiest dial to turn. But that, for for illustrative purposes, I think that's very true. But in the real world, we're excited about balanced mix design because we think that it is going to really open the door for more innovation in our project work, and that's going to create better products for agencies, and it's also going to potentially create more profitable operations for contractors. So with that kind of as a background, at this time, I'm going to hand off to Nathan Moore as our subject matter expert on this particular topic here at NCAT, as one of our subject matter experts, and he's going to take it from here.
Without further ado, I want to talk about sort of my own experience in terms of BMD kind of lessons and tips and things like that. So first of all, welcome. Thank you everybody for showing up. I think we've got a good webinar for everybody today. We mentioned earlier that Phil Blankenship is going to be our guest speaker on this as well. And the last time that Phil and I got together on one of these, we were with Buzz in a pickup truck on the side of the road, paving test sections at Min Road, and we were able to overcome our technical difficulties that time. But we sort of jokingly call it carpool karaoke. We were kind of all piled in a truck together and kept going. So it worked out pretty well. So yeah, so today we're just going to be talking about BMD tips and tricks and lessons learned, and sort of starting from the bottom, basics, all the way up to more advanced techniques. And I think another way of framing this this webinar is sort of, well, how do I get the number that I need? That's sort of what most people ask is, I have a target I'm trying to hit. How do I achieve it? So I got a couple lessons that, when Buzz asked me to do this, I started thinking, from the simplest, kind of the ground up, how would I recommend doing this to somebody? And so my first lesson, and honestly, this is lesson number one. And like they say in real estate, you have the most important thing is location, location, location. And in balanced mix design, it's specimen prep, specimen prep, specimen prep. This was the subject of last month's webinar. Adam Taylor and Tanya Nash just delivered a killer webinar. It was awesome. Lots of great information in there. I'm not going to rehash the whole thing, but I do feel a little bit hypocritical if I did not at least mention it here. I don't think we can talk about balanced mix design from a laboratory perspective if you don't talk about specimen prep. It's really part of everything that we do. It has the largest impact on test result reliability and repeatability. So I have a couple of quick examples. For those of you who, we invest in our company's 401ks or 403bs, or we have Roth IRAs, you follow the market, you know the rule, right? They say it's not about time in the market. It's not about timing the market. It's about time in the market, and not to try to guess, when should I invest money and when should I not? I'm pretty sure though, if Warren Buffett was a part of our industry, he would change this quote and it would say, it's not about timing the oven, it's about time in the oven. And that is so important when it comes to specimen preparation, to pay attention to these small details, the things that maybe didn't matter as much whenever we were doing volumetric mix design or quality control at a plant. I can speak from experience. There's been times where I've left my design pills in the oven 30 minutes, even an hour longer than what I would typically do for various reasons. And I got the same air voids or GMB results as I probably would have gotten had I compacted them an hour earlier. That is not the case, though, with balanced mix design. What I'm showing you here is the exact same mix prepared two different ways. And I'm calling it method one and method two. And I've given you sort of the steps above that. Method one, what we did is we had a bucket of plant mix. It was sampled hot. We split into testing samples, similar to how you can see sort of on the left side here. We split them into testing samples, so about 2,500 grams roughly. And then we pulled samples for a rice, and then we ran a trial weight, and then we compacted. But the idea here is we just went ahead and split out the entire bucket all at one time, and then we would go and get our GMM and our trial weight. Then we compact. Well, we ran the ideal CT and we got about a 32, 33, something like that on average. Well, then, and that is not our typical lab practice, by the way. I did this on purpose to kind of show, I want to know the effect of this. Our typical practice is what I'm calling method 2 here, and that is where you have a QC sample, and maybe it requires you to take an extra bucket out there with you. But with the first set, I would run my rice and a trial weight. All the while, the majority of the mix, especially the mix that I'm going to make my balanced mix design specimens out of, is still sitting in a bucket. It's in the oven, it's staying warm or hot, but it has not been split into testing size yet. Well, so I did this where I pulled a sample, I split it, I put the majority of it back in the oven after I ran it through a mechanical splitter. The other set, I ran a rice, a trial weight. Only after I got those results back did I split, and then I began compacting immediately. One of the benefits of balanced mix design is you don't have to wait to get to compaction temperature to make these specimens. They need to be workable, but they don't have to be at compaction temperature. And you can see here the difference between those. Method 1 specimens, they sat in the oven for about an hour to an hour and a half longer than method 2. And just that amount of time, about an hour, as long as it took to run a rice with 2 replicates and do a compacted trial weight, cool it off and bulk it and get all that information back, it produced statistically different results. You're talking a difference of 32 to 48 or 49 based on the height of those bar charts. So this is important. This specimen preparation is so important, and I could talk about it for Adam and I could talk about this for days. The question, though, is which one of these is correct, right? And that's sort of, there's not necessarily one correct method. The point is we need to pay attention to the differences here. And so if you're finding yourself getting lower results, especially in comparison testing, this is the first place I'd go. We make the mistake of, in performance testing, of sometimes bringing some of our old habits with us that we had whenever we were doing super pave or Marshall compaction, where we're thinking to ourselves, this probably doesn't matter, right? And we got away with a lot of stuff whenever we were just making gyratory pills or banging out Marshall samples. You could get away with quite a few. As long as you had your temperatures right, you were fine. It doesn't really matter how long it had sat in there for the most part, right? But as you know what happens when you assume. Oftentimes, if you're heating your wrap different and thinking it doesn't matter, if you're cutting samples and the temperature is different, or you're going too fast, or if you're reheating binder a lot, these things that may not have mattered, they matter now. So I won't talk any more about specimen preparation. Again, I think it is the foundation of everything that we do. So if we go back to the original question of how do I get the number that I want? If you're not getting the number that you want, that's the first place I would look. And if you're trying to do a balanced mix design, before you just start throwing samples in an oven and going to town, you really got to make sure that you're thinking about specimen prep, which then helps me transition to my next lesson, which is practices make perfect, right? And this is really all about lab practices. I think specimen preparation is a part of this, but I'm sort of making it bigger now, thinking about things like equipment. What kind of load frame do you have? Does the load frame that you have, that you're running, we're assuming you're running ideal CT or iFit or something like that, does the load frame that you have, is it capable and suitable to run the tests that you're trying to do in whatever state you happen to be in? Maybe it's your gyratory. Is your gyratory in calibration? Are you, especially if you're cutting samples out of the middle, are you getting a density gradient through your specimens so that specimens compacted on the top are always denser than specimens compacted on the bottom? Those kinds of things are important. Maybe you're using wheel trackers. Are you making sure that those are in calibration? Especially things like temperature, as those rutting tests are so sensitive to temperature, if you're Hamburg wheel tracking water bath, if it's telling you it's 50 degrees Celsius, do you know for sure it actually is, or have your temperature thermocouple started to drift a little bit? Ovens are so important. What kind of ovens are you using? How much time are specimens spending in ovens? We have problems all the time here with making sure that our oven timers are set correctly. Adam talked quite a bit last month about oven timers being your best friend when it comes to making these specimens in a repeatable way. But are your ovens set up correctly? Have you noticed a difference between maybe one oven or another? Do you have good calibration records on all these things? But maybe talking about comparison testing. So many of the attendees online, you may work for companies that have multiple plants or maybe different labs. Have you run internal round robins inside of your own plant to make sure, inside of your own company, to make sure that you can produce the same results? If you cannot get the same results inside your own company, well, you're not going to be able to, you don't stand a chance at getting the same results as your agency does. Have you done internal comparisons with one another, or even historical comparisons? If you start getting, if your results deviate from where you expected them to be, how did you get those expectations? Did you get them based off of good data? Have you done a root cause analysis of why maybe your results are not what you think they are? I mean, there's been examples in my own work where I had a mix that I thought for sure was going to pass a certain threshold. It did not. And it turns out it did not because they were batched inappropriately, or my oven was off, or sometimes they're more simple, but other times it's things like, well, I thought I was using one material, but I was actually using another. You need to go back to those kinds of questions before you start to panic about getting a weird result. You need to look back and figure out, well, how did you get to where you are? A couple more points. Data storage. This is really important if you're trying to just get your feet wet and understand what happens when I pull this lever or twist this knob. How do my mixes respond to mix adjustments? Well, are you storing your data in a cohesive way, and somewhere where you can compare and contrast mixed results easily, as opposed to fragmented and all over the place? Are you making sure you're recording the meaningful information? I can tell you from our own practice, when the ideal CT test first came out, we were really only recording the ideal CT number and maybe the peak load. Well, now we're recording peak load. We're reporting the slope at 75% of displacement. Of peak load. We're recording displacement. We're recording failure energy. We're recording all those things, because you never really know when those things are going to end up being important, and it's always better to have the data. And then finally, training. Are you specimen prep again? But are your technicians who are making specimens, are they trained appropriately on how to do that? Are you trained in data analysis? You don't have to have a PhD in statistics to be able to do some of the more simple basic stuff to compare data appropriately. How do you know how big of a difference is enough? Those kinds of questions, I think it's useful when you're trying to do data analysis. And then also materials knowledge, I think, is important. Some people, if you're like myself, we have binder engineers here who know. Pamela Turner has forgotten more about binder than I will ever know. But sometimes if I'm getting a strange result, it's useful to know, well, maybe it's got something to do with a unique material that I've started using that I don't really understand. So I'll give a brief example of this. A couple of years ago, we launched a project here just internally in our lab comparing 5 different load frames, wanting to know, do these all produce similar results? Well, we made over 300 samples from 6 or 7 different mixes, and we ran them all in a very repeatable way, had the same technician make all the samples the exact same way. And then we ran the ideal CT on all these devices. And what we found is we started to compare them to one another. So each of these points with the little whiskers pointing out, that's a comparison between these equipment. And all the red ones that kind of fall in that blue band, those represent comparison of two devices that are what we call practically equivalent. And the ones that fall out are not practically equivalent. And what we found out that one particular device was different than all the other ones. And all the other ones, yeah, there were some differences. They weren't perfectly exactly the same, but they were close enough to be determined as statistically and practically equivalent to one another. But then using this procedure, we went back and figured out, well, what was the root cause analysis? Why was this one particular piece of equipment, why was it different than all the rest? And we were able to solve that problem. And then there's an NCAT report about this and a journal paper as well. We proposed a method to determine if your device is equivalent to another one. Once you begin to get some of these more basic ideas, making sure that all of your ducks are in a row before you start to panic about results is really important. And the last thing I'll talk about sort of laboratory equipment is I'm showing you two devices where we ran the IDT on. So this is really just peak load essentially, but then you determine the indirect tensile strength. And peak load is a very repeatable parameter between devices, but I'm showing you an example here of where we noticed that it was not, that we should have had the same peak loads and the same IDTs between these two devices for these mixes. But what we found was that was not happening. And there was a pretty big difference. They should have fallen right on this dashed black line, but they did not. And ultimately, the reason for this was there was a setting in one of the machines that we were running that these peak loads were very, very low, and we had to make sure that we had the correct settings applied before we just started breaking samples. So many people, they want to unbox a new piece of equipment and just start breaking samples, but you need to make sure that you're using it in a way that is appropriate. The third lesson that I'll say here, this is a quote that's often attributed to Leonardo da Vinci, but I don't think anybody really knows. But simplicity is the ultimate sophistication. And then what I mean by this is if you can master the basics, the simple stuff, the material basics, then you're going to succeed in designing the majority of your mixes. I think Dwight Schrute said it a little simpler. Keep it simple, stupid. That's really the point here, though, is before we try to move on to more complicated solutions, we need to make sure we understand how the basics of aggregate blending, of mixture volumetrics, of the effect of time and temperature in the oven, those things, if we can understand how those apply to each and every situation, that is the best predictor of success, in my opinion. So this quote on the top, this is a quote that I live my life by, is when faced with a problem with multiple solutions, begin with the simplest approach first. So let's give an example. Let's say you have a failing mix design and you're running the ideal CT and you need 15 more CT index points. Well, how do you get them? The first thing that I would do is I would look, well, are my data repeatable? Am I getting consistent results? Do these results make sense based off of a historical knowledge or based off of experience? If the answer to these questions are no, well, start there. Don't start swapping out materials or purchasing additives yet. Fix this problem first. Well, if the answer to this question is yes, well, then we move on. Well, maybe we can change the gradation a little bit. Maybe we can open it up and allow for a little bit more binder in the mix. Maybe you have access to multiple wrap sources, and you can swap wrap sources to a wrap that's slightly less stiff for whatever reason, and that might get you the movement that you need. Maybe it's an aggregates change. Maybe you can start using aggregate A versus aggregate B, more angular aggregate, or more rounded aggregate, or different sizes. Changing the gradation by swapping your aggregates from dense graded to slightly more gap graded. These are all things that have worked in the past that don't require as much effort or complexity to solve the problem. Well, let's say that none of these things are an option. Well, then we start looking at identifying different binder sources. You may be in a region where everybody around you is selling -22 grade binder, and maybe you're looking at getting a -28. And maybe that's not as easy to find, but if you've worked your way down here and you realize that the simpler approaches don't quite work yet, well, then maybe you try to identify a different binder source or a different binder grade. Heaven forbid we decrease our wrap contents, right? But maybe that's required. If maybe that's what you have to do in order to get the design to pass. And then if those things don't work, well, then maybe we're talking about different additives or fibers or oils or recycling agents. And I'm not at all saying that these things are bad. And I'm definitely not saying that these things should be used as a last resort. That is not true. What I am saying is that start simple and add complexity as needed. It is amazing how a simple gradation change to tweak to make more space in your mix sometimes can solve the problem. And all of these things may solve the problem, but the biggest question is, what is the simplest and cheapest approach that gets the job done? Getting the job done is the goal. The simplest and cheapest approach is the method. And whatever method it takes to get there, that's what we want. But start simple and add complexity only as needed. So here's an example of that. I just wanted to show you, this is something I've learned, and this is not gospel truth. This is not hard and fast rules just yet. But I'm looking at plotting CT index versus asphalt content on the left versus CT index versus the volume of effective binder on the right. And what I have found is that in many mixes, this doesn't happen on all the mixes, that adjusting the gradation will affect your VBE, and VBE may be a better predictor of CT index than asphalt content. Because this right, and the one on the left, this is not really a linear trend. You can see it's kind of got a curve to it. Whereas the one on the right, that curve is kind of flattened out a little bit better. Now, this requires you to go and measure VMA to do this, and my own boss would tell you that VMA is unreliable. I tend to agree. VMA it can be an unreliable target. That doesn't mean it's not a good tool, though. There's variability in VMA. There's variability in this plot. But the idea, what I'm trying to get at, is going back to basics, and that is understanding that volume of effective binder is the difference between VMA and air voids. And as that difference grows, your VBE grows. VBE is so important, making sure that you have effective binder to add flexibility to your asphalt mixes to prevent cracking. This is really a building block of that. And maybe a gradation change can solve the problem without you having to go and purchase new material. So don't graduate past the basics when doing balanced mix design. And the last point that I'll make, and I'll tee it up really for Phil, is looking at wrap content and binder content. So I still kind of count these things as some basics. I know we don't like decreasing our wrap content, but I'm showing you here a plot of binder content, and this is rutting results. 35% wrap and 45% wrap. So as you move from left to right, you are increasing in wrap content. Well, look what happens to your Hamburg wheel tracking rut depths as you increase wrap. Your mix is getting stiffer. Rut depths are going down, 3 to 2.4, 4 to 3.2, 4.7 to 3.8, and that makes sense. Again, basics of asphalt performance, stiffness should influence rutting as expected. And the same thing with binder content. 4.3 to 4.8 to 5.3. As you increase your asphalt content, your rut depths are going up. So 3 to 4 to 4.7. And again, this makes sense. This is exactly as we expect. So like my point here is that sometimes it's the simple things that can move the mix. Now, the question then is, what if simple isn't enough, right? What if we've done all these things and you're not quite getting the result that you need? So that's where I'm going to hand it over to Phil to see, he's got some more things to say about that.
Yeah, just a reminder, if anybody has any questions, you can put them in the chat box. Simple ones I'll address kind of as we go, or me and Nathan will address as we go. Any that we feel merit or good for discussion, we may save to the end of the webinar and then discuss them, discuss them live with the audience.
Okay, thank you, guys. Good morning to everyone, and appreciate team down in NCAT for allowing me to join in. Just want to add on to what the guys have been talking about. Nathan, appreciate the comments about about lab repeatability. It all starts there, and you sure can't make decisions on moving things forward in a laboratory until you get the error out of the laboratory. Otherwise, you feel really good about a number, and then the next thing you notice is that you feel really bad about it the next day if the error goes the other way. What I'd like to do is just hit on a few items as we just to add on to that from the mixture side and looking at modification of the mixture. You all probably, some of you may have seen this before. Good guy named Randy West and folks put this together. And this was a pavement survey this was a survey that was done through agencies trying to understand, what are we looking at today that causes our problems. And we know that cracking, and the reason I put this up there is cracking is the major focus. So when we begin to talk about BMD tips and tricks, most of the focus right now is on ideal CT or SCB or something similar to it. What I do want to add is a word of caution with that is that realize that mixtures also do not let the Hamburg rutting always be rutting in your mind. It could very well be stripping. We've seen that in various types of materials. And so it's important to look at that stripping slope of the Hamburg device as you get into your mixes and realize that what you're thinking may be rutting could actually be stripping. So if you're trying to take it from one way to the other and you end up with a rutting problem, realize that sometimes the fix could be simply as much as putting anti-strip in.
Hey Phil, you may want to turn your video off. Your bandwidth is kind of low.
And I've got a sort of a summary here at the end. Is my voice coming through okay, Nathan?
Yeah, your voice is fine. And I think
is that okay?
You turn your video off, yeah, you're good.
Okay. Yeah, if it's not, just please let me know and I can switch over. Thank you all. Doing this remotely. So again, thank you NCAT for your patience and letting me jump on today to be with you today. So, what improves ideal CT is what we're trying to understand. What improves Hamburg? Some of you all may be using an APA or other tests. And then what are the compatibility issues with these? Something I will say is that and the writing with it, water, helps you stabilize the temperature, but it also will help you understand the stripping component. I do like ideal RT or the hot IDT for quality control. I like the Hamburg for the design, but I like when you go to the field to have something like the hot ideal CT or the hot CT or the RT is what it would be called today. Moving on. Things that I look at is there's several different products that I work with, and these such as and aging. That's the two big ones I cannot hit enough. Is that asphalt content and aging drive BMD. But what happens if you've done everything you can to your mixture, and now I'm sitting here, I can't get the dust out of my mixture, I can't, I don't have any more room for asphalt where I'm going to fill my hamburger, or I feel really good where I'm at on my CT, but I've just got to make some other adjustments to take my mixture to another level. Fiber at all. It's a strength fiber. So here you see where, but now I'm using it with a polymer modified asphalt, and I go from a single to a double, and I even get more of a bump. Why is that? Well, that's because my polymer is adhering more to that the fiber.
On the previous slide, yes, on that one, what I was trying to hit on that one was that two major factors that's going on with this slide. One is if I put in a bio oil, I greatly increase my ideal CT. But again, it's got to be an approved product that's going to be used through the state or local agency. The other thing that I pick up on this is that if I do aging, and this is only 6 hours of loose mix aging that I did on this, I did the aging in order to understand, you know, what the bio oil does. But more importantly, look what it does to my ideal CT. Anytime you put any of these products under heat, you're going to lose the light ends on it. So if you're 15 minutes too long in the oven, 15 minutes too short, or not enough time in the oven, it will really mess with your ideal CT. Or that would go if you're trying to do a verification in the field, validation in the field. It's time in your silo. It's time in the truck. It's time while it's hot through the paver. We can go on to the next one. On this one, one thing that I did on this one, this was a study where we were looking at ideal CT results with a 6422 source. And just trying to help, actually at the time I was showing it to Kentucky, helping them understand the difference, and not that everybody should not just be testing at 25C. We need to be looking at other temperatures. The other thing that you pick up on this, notice I have a 6422. There's a lot in this slide. And I have two different crude sources in this one, two different crude sources. Not only on the blue line and the red line do my crude sources make a difference, but the testing temperatures we know can have a huge difference. And so make sure your bath water is correct. Make sure that as you take it out of your bath water, it's not sitting on the table. Go directly, or if you're just in a conditioning chamber, go directly into your test device and run it. At the same time, if you're having problems with one crude source and you have an option of looking at another one, check what's around you and see what's available. Okay. We can, yeah. I show this one just to understand about the high wrap samples that we're looking at. In this case, where I've done some mixtures with high wrap, and I'm calling it like about 45% wrap, we looked at aging again. And what I pick up on this one again that I try to show on this is understanding one, time in the oven. Look what it does to your ideal CT. That's where my focus is on this one. And the other thing to pick up on this is understanding what the wrap does and how it begins to lower my ideal CT. So I've got to have to put something in the mixture as some type of bio oil or aromatic oil to offset what's going on with the aging. I saw a question pop up there, Nathan, about how many samples that we used with ideal CT. We're running usually we're running minimum of 5 and sometimes about 7 to 8 through the laboratory, throwing out a high and low, but minimum of 5 on an ideal CT test. Let's go to the next one. This is where I want to focus, and then we'll leave it here. I throw this one up because this one has helped me. This is Phil's opinion, and keep in mind this is Phil's opinion. Everybody's going to have a little different opinion on this. On the left, I've got the different factors from increasing AC, lowering a PG, making the PG go higher. And then going across, I've got an ideal CT. You could substitute in that SCB if you want. Hamburg in the middle, or APA. And then what's it going to do to my density? What's it going to do to my density? And the pluses are meant to mean that it's going to be it's going to help you. The minuses are mean it's going to it can take it the negative direction, and of course more pluses is even better. So with that, what I wanted to look at on this one is just let everybody just take a look down through the list and look at what, for instance, time under heat in an oven will do. It's going to kill your ideal CT, but really help your Hamburg. Density, it really won't make that much of a difference. It's somewhat neutral on that. But if I have a high absorption aggregate, again, it's going to hurt my ideal CT, help my Hamburg usually, and density. Yeah, it can make it difficult if all your asphalt begins to absorb into your rock. I look at aramid fiber. It will help ideal CT. It will help Hamburg. Density, the question is out. I've heard people comment that it will help density. And if it did, it was only helping it by holding the edge. It doesn't make it pave easier. It helps you hold that edge of the pavement to keep from lateral movement. But what does things such as a thicker pavement mat do? Well, we know it's not going to help your ideal CT or Hamburg, but it greatly helps your density. So little things in here, and I hope this helps just to give you an understanding of what these look at. One of the other ones just to point out before I leave that slide is the recycling agents, such as the bio oils. Again, helping ideal CT will lessen your Hamburg, and it should help on density a bit. Is it really noticeable? I don't know how much. People have claimed it makes it a little easier to pave, and the paving and understanding what it's like under the roller is so difficult to quantify. Just the last slide I had, Nathan, one more just to have a little fun. I work with interlayers from, if you go to the next slide, I get to, well, let's move on to the next one. Couple more through right there. I get to work with interlayers, and I thought just so folks understand, I throw this one in there. I know we like to talk about coarse mixes and fine mixes. This is pushing it to the extreme, and these are legitimate ideal CT numbers. If you're looking, I'm testing at 20, 15, and even 25C with different binders in it. What I've done here is I've taken a mixture that's like the thin lift mixture that you hear about a lot, the 4.75 mixture, but I've put a lot of asphalt in it, 8.5%, taken the air voids down to 1%. And this is meant to be used as an interlayer for crack absorption. And so look at what is possible when I take these mixtures and I throw it to the extreme. And we can push these mixtures up. How does it do in rutting? It's about 5,000 to 6,000 in a Hamburg. It's not meant to be incredibly rut resistant, but it will hold up to traffic. So I thought I would throw that in there just to let you see what gradation changes and the like. So that's all I've got, Nathan. I hope that's been beneficial. And sorry, folks, for the connectivity.
Yeah. Do you want to talk about anything else?
Oh, yeah, my closing slide. All of this comes at a challenge when we have to push and evaluate sustainable options, and as we try to make our mixtures and we try to understand the cradle to grave and the low CO2, it's all happening at a time that we're trying to fix our mixes and make them better. So, boy, you talk about another balancing act is BMD versus sustainability, and we can do it. We can do it. It's just a challenge. Thank you, Nathan.
Thanks, Phil.
Well, thanks, guys. That was some great technical content from two different perspectives. So my job now is to kind of pull all that together and give you some high value implementation takeaways. And I'm very excited to do that now regarding this topic. And the first thing I always want to state is that balanced mix design with relaxed volumetrics, we have to loosen our grip on legacy volumetrics. It can make mixes better, and it can spur innovation at the same time. And that's what we really want to do. We want to kind of get away from recipe specifications and open the door for higher quality and more innovation and really smarter life cycle investments and more sustainability and all those types of things. So getting into the content that Nathan shared, there at the beginning, reliability and repeatability are a function of specimen preparation. That is extremely important. And if you don't have well practiced, consistent practices in specimen preparation, it's going to have a negative impact on reliability and repeatability. And the data is not going to be is not going to mean what you think it means necessarily in terms of your interpretation. Practice is key to this. You need to practice with your equipment, practice with comparison testing. You need to put have a well thought out plan for data storage. I'm an advocate of not just recording a number, an ideal CT number for a mix, but record the three parameters that make up the ideal CT equation: the area under the curve, the downhill slope, and then the displacement at the point where you measure the downhill slope, and also the peak load or the strength from that test. Store all that data so that you can do parametric studies and determine, hey, when I make changes, what kind of outcome is it producing? And then lastly, training. You know, it's not just about you designing a good mix, but your QC team, all of your technicians, everyone has to be on the same page when it comes to how can we optimize our reliability and our repeatability in our data. And like Nathan said, remember the basics. And the kind of the starting point for this is that we really need a healthy, effective binder content. The binder that's active in the voids has to be a healthy binder so that it can provide us with ductility as opposed to brittleness. And the basics, the things that we know about really designing mixes from a volumetrics point of view, like VMA, we don't need to forget those things. Those tools are very useful for developing healthy mixes. They just have very limited practical use in policing healthy mixes at the time of construction. As Nathan said, start with the basics. Start with gradation. Start with your wrap. Optimize your lab practices. Use those things to improve the numbers that you're getting in your design process. That's kind of step one. And then if you don't achieve the outcome that you need with those basic steps, then you can move to additives, binder sources, and other solutions. And that gets into the content that Phil provided very well in his part of the webinar. And when you do that, when you go to the additives and you go to the other things, kind of at step two, and you start turning those dials, that's when you can get into your own parametric studies with your materials in your lab, with your resources, to say, okay, it's not just about putting 0.5% more binder in the mix or 0.75% more binder in the mix or whatever the need is. If you're just turning the total binder content dial, but how can I turn all of the dials in order to achieve the most efficient cost per ton for this mix to meet the requirements that are published and active in the specification? And I think our presenters did a really good job of covering all of these implementation takeaways. And I always try to end with the statement in these webinars is really about safe and sustainable asphalt pavements at the lowest possible life cycle cost. And I don't care. I was talking to somebody about this just yesterday. And, if you're building a perpetual pavement, every layer, whether it's a surface layer or a base layer or a binder layer, or whether it's a preservation thin lay, every layer in our pavement structure needs to meet the prescribed performance requirements, and it needs to be a healthy mix. And healthy means something different for each layer in the pavement structure and each application. But we think that balanced mix design is going to be the tool to get us where we need to be, and design and build long life mixes and long life roadways. So that is it with the technical content for this webinar. And there's all of our email addresses, Travis and mine, Nathan Moore, and Phil Blankenship. I'm very grateful to the team here for coming together and doing this webinar. We want to make sure we really spread the word on our end of cycle conference that we host at the end of every 3-year research cycle. It is scheduled for May the 7th, 8th, and 9th of 2024. Please put that on your calendar. There'll probably be 250 to 300 people here at NCAT. We'll do track tours. We'll do preservation tours. have a lot of great implementation focused technical content, and of course we'll also have some great fellowship. We also like to promote the training in your pocket, which is the product that Travis developed here for NCAT, and this is, you can get all this through our YouTube channel. Very short, very concise, very entertaining and amusing short videos to help your new technicians kind of get their feet under them and begin to do a good job. Now, if you want to learn more about balanced mix design, Travis is our training coordinator. He offers some really good classes, and some of those are at NCAT. Some of them can be at your location. But if you just go to ncat.us and click on education and training, you can see what those options are. And here at the very end, the last thing I like to say is promote the next webinar. And so the next one is November the 16th from 10 to 11 Central Time. This is another one. Of course, I guess I always say that I'm excited about it, and it's true because I am. But dialing in an asphalt plant with minimal tonnage is a subject that is very near and dear to us, because we go through this process every 3 years when we rebuild the NCAT pavement test track. So I'm going to now turn this back over to the rest of the team, and thank y'all so much for participating today.
All right. Well, thank you again, everybody. I hope we were able to provide some helpful content. Adam, I see Phil's question. I'll just go ahead and, I'm sorry, Richard's question. I'll just go ahead and ask him. Richard Steger asked me, after the work we've done with IDLE CT, do you have an opinion as to what equivalent should be for this test? And for those of you who aren't necessarily aware, that's the idea of how close is close enough? How close is practical, where we can say that these two devices are practically the same? And so, Richard, I know you and I are working on this in an ASTM subcommittee, but my understanding would be, if you've got the 95% confidence interval of your mean, if the whole thing is within one standard deviation of each other, I know that maybe, I think that is probably where I would start. It doesn't mean that every single replicate has to be, as you're aware, but are your means within one standard deviation of one another? That's probably where I would start. I think we were able to achieve that in the study that I did, but I'm willing to be, as we start working on that ASTM spec, to maybe readjust that.
There's one additional comment that just came in from Bob Sifford, complimenting Phil's table showing the effect of different strategies on IDLE CT, Hamburg, and density. It says that his team has done a lot of work around reducing production temps with chemical warm mix, and it would be nice to incorporate that in the future to show how production temperatures affect performance testing results, essentially.
Yeah, that's a great comment, Bob.
That's a great point.
Go ahead, Phil. I'll let you comment, and then
I was just going to say that's a great point, and naturally, anything we can do to lower the production temps is going to help IDLE CT. It lowers aging, lowers absorption into the aggregate. So absolutely, and of course, the effect on compaction at the end of the day should be neutral if it's as a warm mix additive. So excellent point.
Yeah, and I'll just add to that, Bob, where we've actually begun some work. There's a case study that we did looking at laboratory work about using warm mix additives at lower temperatures in the laboratory and seeing the effect of that on IDLE CT, but also overlay testing. And I think it was pretty eye-opening work. And that sort of served as a launching point to where we're going to begin doing some field evaluations on that exact question. Because I agree, that is, it's a great opportunity to really merge both sustainability and balanced mix design mixture optimization. It's a great point.
That case study you reference is actually published as part of the NAPA BMD resource guide. So
it can be found online.
It's currently on the NAPA website.
Yep.
Okay, I'm not seeing any additional questions or comments. Yeah, I think we've covered just about everything, fellas.
Well, thank you again, everybody, for your patience. Again, we are excited to have you guys here, and hope to see you guys in a month as we talk about asphalt plants.